All right, hello, AP Statistics. This is section 9.3, type 1 error, type 2 error, and power. Okay, in reality, this is not really 9.3. This is just a section that covers 9.1, 9.2, and 9.3. It's inclusive in all those chapters. However, I really don't like discussing this until the very, very end. These ideas appear in all three of them. However, I think they're better understood if we go through what is a one proportion z-test and a one sample t-test. Once those are finished and satisfied, and we understand those well, I feel like it's better understood to then discuss after a type 1 error, a type 2 error, and what power is. Okay, so if you have a graphing calculator, you have your note sheet, you have a piece of paper and some pencil, you will be ready to go. Okay. All right, now here's the story. Miss Moon, a popular math teacher on the campus, would like to be on my bowling team. Okay, and I told her, if you want to be on my bowling team, you're going to have at least a 200 average. Okay, now what is a 200 average? When you bowl a full game, the highest score that one could possibly get if you knock every pin down is a 300. Okay, so having over a score of 200 is actually very, very good. And so I shared with her, do you have a 200 average? And she said, not only do I have a 200 average, I have a 206 average. Okay, and she actually gave me her population data over here to the left. Okay, and here she showed me all of her games for the past 2 years, and this represents 180 different games. Okay, and you can see they are titled off to the left here, games 1 through 10, 11 through 20, and so on, all the way to 171 to 180, and the respective 10 scores for each row are counted to the right. Okay, now I could, if I wanted, take all these members of her population, every single one, all 180, put them on my L1, do a 1-bar stat, and see if it's actually 206. Okay. However, I don't want to do that. Okay. I just feel it's too many. And what we decided to do instead was just choose 15 random bowling scores. Okay. There is some suspicion that maybe she just wants to be on my team. Okay. And she is giving an exaggerated high score. Okay. So that she could be on my team. And I don't know if her average is really 206. I think it's actually going to be a little bit less. Okay. So again, we have 180 games. We randomly selected 15 games that we need scores for. So if I look at this 4 here, what that means is I'm going to go over to games 1 through 10 and count over 4. 1, 2, 3, 4. And I've got 137. I'm going to put that score right here. Okay. And then I'm going to go to game 8. That's still under the row 1 through 10. That's 171. Okay. 127. That's in the 120s. That's in this row. 1, 2, 3, 4, 5, 6, 7. That's 175. Okay, and we'll continue this all the way through. Okay, my students have access to this as you do right now. So this is 154. This is 172. This is 148. 152. 174. 189. 166. 160. 139. 162. 166 and 142. All right, I'm going to double check this just to make sure I have these all right. And 166. And then what I'm going to do is once I'm confident these are correct based off what I have over here to the left, I'm going to put them in my graphing calculator in L1. Okay, get a sample representation for her mean, and we'll see how that compares to her population mean. Okay, and see if it's statistically significantly different from this 206 that she is claiming. Okay, so in order to do so, I'm going to make an alternative hypothesis. Okay, and so there's my null, there's my alternative. And she claims her average is 206. So we're going to write that as our null. And it is my belief, okay, just because my team is real popular and that she really wants to be on it, that's her average is truly less. Okay, and I'm going to find mu as the population, the true population mean bowling score for Miss Moon. Okay. Now, if you looked real quick on the other slide, Okay, and I actually said the conditions are met. Okay, but we'll do this real quick just to make sure that we know that this is fair. It does say random. That is my first condition. All right, so we'll go back. It is random. That was stated. So that's good. Second one is the 10% rule. Now, she had 15 games as part of her sample, and that is less than or equal to 1/10 her population of games, and there were 180 that were listed. Okay, so that is satisfied. The third is large counts. Okay, and if you were to do the large counts, what I did is I took my 15 that she provided, and I made a a box plot with that, and I got a picture that looked like this. Okay, and so these are for her sample of 15 bowling scores. Okay, and you'll notice that there are no outliers amongst her 15, and no strong skewness. Okay, and so what does that mean? It means our conditions are satisfied. And again, I already told you that. If that's the case, you don't typically have to work it out, okay, but it is there, okay. Now, I told you I did a one var stats, okay, and again, my conditions are satisfied. That's actually hidden underneath my title. Sorry about that. And it looks like this, okay, so we have an X bar of 160. This is an important piece of information for us. Okay, and then my S of X is right there. That is my standard deviation of my sample. Okay, and we know that N is 15. So, and it actually shows that one more time. Okay, so we know degrees of freedom is N minus 1, so we have 14. And this is the setup for it. Okay, so I did a little bit of the work ahead of time. We're doing a T statistic because, again, my population standard deviation really isn't known based off what was given. Okay, it wasn't shared with to me what that data piece was from this moon. She just said that her average was 206. Okay, so we did a sample standard deviation, and that's the 14.971 that you see in the second piece right here. The first item is the mean, and that is located in the first position. This is her X bar for her sample of 15, minus 206 over, again, her sample standard deviation divided by the square root of 15. Remember that this is called a standard error. Okay, and if you were to draw a picture, do my best to draw that. Okay, what we have here is a mean of 206. Sorry, it's a little tough to read. Her standard error, if you divide that out, okay, I've already done that for us, is 3.865. Okay, so if I subtract over 3.865, that is 202.135. Okay, and if you consider where her mean is 160, that's like way down here. Okay, and I'm not even drawing this to scale, but the 160.467, it's super far down here, and you are shading based off our alternative here to the left. Okay, so this says shade to the left, and you can see that there's not much area over there. Okay, nevertheless, I will still do this math. Okay, negative 45.5333. That has a hat on it, divided by 3.865, and you get a T that is equal to negative 11.779. Okay, now through our practice with 9.2 and 9.3, there's kind of an understanding here that when your T, I'll just say your absolute value of T is really bigger than 5 or 6, okay, and as long as you're shading in the direction that your alternative shares, and it covers just basically the tail of the small tail of your normal distribution, that your proportion is going to be about 0. Okay, it's going to be 0, and because of that, okay, we're going to write a conclusion. Okay, and what we're going to say is that we're going to reject the null because our p-value, which is about 0, okay, it's not exactly 0, so maybe it's fair that I put this little squiggle in. Okay, but even if I rounded to 4 place values, it's 0, 0, 0, 0. Is less than, we'll say, an assumed alpha cutoff of 0.05. And what that means is there's evidence to suggest that the true population mean bowling score for Miss Moon is less than 206. Okay, so she is a dear friend, you know, and based off this sample, I'm looking at Miss Moon and I'm saying, you are a liar. Okay, and I do not allow her to be on my team because I think she will just weaken it. And I just call her out and say, you know what? Can't have you on my team. Plus the fact I'm kind of angry that what was suggested here kind of means that you were kind of being dishonest with me. Okay. Now, what happens further, okay, is what Miss Moon shares. Is she says, you know what? My actual population moon average is 206.3444. Okay, and if I look that up, okay, on the graphing calculator and actually put all 180 scores in my L1, this is actually true. Okay, and this is her population standard deviation. Okay, so what does that mean? Well, here's what it means. Imagine this. Okay, this is a population representation of all of Miss Moon's bowling scores. Okay, and her average is 206, which means that most of her scores are somewhere around here. Okay, and there's going to be some that are a little higher, but not as many. Okay, because again, 206 is the average, but there's going to be moments when she has some that are higher, and some that are really high. But again, the frequency of those won't be as strong. Okay. And they tail off to the right. And there's moments when she has some that are a little bit weaker. But again, when 206 is the average, okay, the representation of the ones that are weaker are not as frequent. Okay, so this is really what her, imagine 180 dots representing all 180 scores. Looks like this with 206.34 right down the middle. Okay, now while our scores are random, okay, in terms of how we were chosen, there's going to be moments when we make mistakes, okay? And not in terms of how we choose them, but sometimes our random numbers don't truly represent this full pool of data that you see off to the right. You know, maybe the 15 that I chose randomly just happened to be ones that were more represented on the left-hand side. Okay, and what does that mean? That, you know what, we didn't purposely do this, but the random sample that we created was actually not representative of the population, and it gave us a conclusion that wasn't accurate. Okay, so does that happen? It does. Okay, it's called what we call a type 1 error. Okay, so I have these listed here, type 1 error, and that's going to go in here. Okay, so notice I rejected the null. I rejected the claim that her average was 206, and it was actually true. Okay, and this was a type 1 error. Okay, and it just means that while we had good intentions about our sample, okay, and may have chosen the numbers randomly, sometimes it doesn't give us data that supports the truth behind what the original claim is. Okay, so type 1 error, and I'll put that in words there. And this is from the textbook. It's well stated. It says when we reject the null hypothesis, when in fact the null is true. Okay, so we thought that her original claim of mu, we rejected the null, okay, which was that her average was 206, but it was true. Okay, oftentimes they'll ask for a consequence, like what was the consequence for making this mistake? Okay, one, I may have lost a friend because I called her a liar. Okay, you may have lost a friend when she was actually being truthful. Okay, second thing is that I may have lost the opportunity of having a great player on my team. Okay, so lost opportunity to have a great player. Okay, so yeah, so that's a big mistake, not only just with the math, but kind of the humanity behind it. You know, I thought she was being dishonest. It kind of killed the friendship there, and I let her know, you know. So, and deep down, she was truthful. And again, the second piece is that we lost an opportunity to have a good player on her team. If I want to improve my team and make my bowling team strong, she certainly would have enhanced the skills on our team by her, you know, ability to bowl well, and I reject her, okay, because I actually picked a wrong set of data. Okay. All right, now it could have gone the other way. Okay, sometimes we have moments when we do not reject the null. Okay, meaning we believe the null to be true when actually it's not. It's actually false. Okay, and so that is actually down here. That is actually a type 2 error. Actually, I'll write it like this. Okay, and again, the book will describe this. It says when we fail to reject the null, when the alternative is true. Okay, so we do not reject the null, and actually the null is false. Okay, and actually the alternative is true. And they like to emphasize this part of it. Okay, we more or less like to say the alternative is true rather than always saying the null is false. It's really kind of emphasizing that our alternative, which was our secondary thought about what was originally presented, okay, was actually the true idea, okay? And let's assume that was the case. Say I got data. Let's pretend for a moment that this wasn't true, okay? Say she said something that was false, but I found her results to be true. What's the consequence of that? Okay, maybe I had a person on my team who didn't belong there, okay? In the sense that I thought I had this quality athlete who was gonna be part of the team, and help with victory when deep down her scores weren't as strong as she said. Okay, so if that was the case, okay, where we didn't reject the null when the alternative is true, we may have had a person we thought was a strong player. Okay, and not just a strong player, we'll say a strong bowler when she was not. All right, and that may hurt the team. You know, like when we were going to a championship game, and again, she's a ringer that we're bringing in because she says she has this great average, and in the end, it's like, wow, you weren't nearly as good as you said you were. Okay, and so that would be a consequence of this moment. In context here, when we fail to reject the null, that means we failed to reject the null. So the average was 206. Okay. If we fail to reject that, okay, that means that we did not reject the claim that her average was 206. Okay, but the alternative was true. Okay, her average is really less than 206. Okay, so that's what it would be if you had to put that in context. That's not really what did happen. Okay, this is really what is superior because we actually rejected the null in this case. But sometimes the reverse scenario happens, and again, you can talk about consequences for each, and you can talk about what it means in context to have a type 1 or type 2 error. They'll ask you for both of those at different times, and sometimes they'll actually put them together. Okay, so all right, last thing before we move on. Power, okay? Power is the probability of rejecting the null when the alternative is true, okay? So basically what you're doing is you're rejecting the null when you're supposed to, okay? And that actually fits this box up here. You're rejecting the null when the null is false. Okay, so you're given bad data and, sorry, you're given a bad claim, okay, an incorrect claim, and you have data that supports it versus some alpha cutoff that was provided, okay? So oftentimes people ask, what's in here? Nothing. Okay, there is no name for this location. Okay, so we just leave it blank. All right, now a couple things you need to know about power. Okay, power first. If you want to increase power, you need to increase your sample size. Okay, now think about what our formulas look like, and I'll write the first one here. It's x bar minus the mean over s sub x divided by the square root of n. And the other one, dealing with z from 9.2, was p hat minus p divided by p times 1 minus p over n. Okay, and if you think about your normal curve or your t distribution, they all look kind of similar. And what I'll do is I'll describe this curve with both of these equations. And the idea is this, is that remember that when we find a t score or a z score, we oftentimes mark it on a normal distribution and we'll shade to either the left or the right. Okay, and the idea is this, is that when any one of these test statistics, okay, is further to a tail in either direction, there's a likelihood that it may be rejected, meaning the original null hypothesis may be rejected. So how does that happen? Well, it's when the absolute value of t or the absolute value of z gets larger, okay? And how does that get larger? Well, one way is through the n that's in your denominator, the denominator, okay? So if you think about this n, as n gets bigger, okay, as n gets bigger, okay, this standard error gets smaller, okay? And if this gets smaller, okay, then the entire test statistic gets larger. Okay, and if that gets larger in either direction, when I say larger in the positive direction, okay, that means you are moving more and more to the right, okay? If it's a larger negative value, now let me be careful about how I say that. It's more the absolute value of that negative test statistic, as that will move out more to the left, okay? So, and if that happens, then you move to an area that becomes more rejectionable because this area to the left, or maybe this area to the right, or maybe both together, gets smaller and smaller. Okay, and when that area gets smaller, we assign that to a p-value, and when p-values get smaller, then we reject the null. Okay, the same thing would hold true with this n in that denominator as well. Okay, it's the same purpose and principle. As this gets larger, this square rooted item gets smaller, and the smaller this gets, the larger this fraction gets, and that moves us in either direction, either the left or the right, closer to a tip, which means that we have a smaller area, which means our chances of rejecting against some alpha cutoff is much stronger. Okay. All right. The second thing is to increase your significance level alpha. Okay. If your p-value, for example, is 0.0, I'm going to make this up, 534. We wouldn't reject at an alpha of 0.05. But if I increase my alpha cutoff to 0.10, then we now have a representation for rejecting the null. Okay, so as you raise your alpha level, the chances of rejecting become more strong. Okay. Okay, so what is the probability of a type 1 error? Okay, as you look at that, you're probably thinking, man, this is going to be some big fancy formula. And it's not. The probability of a type 1 error is just your significance level, alpha, whatever you have that assigned for this particular problem. Okay, so if your alpha is 0.05, then this is your answer. You just write 0.05. And oftentimes, if it's not given, we often make the default 0.05. But whatever is assigned to your respective problem, that alpha cutoff is your probability of a type 1 error. Okay. Now, the probability of a type 2 error is somewhat massive. Okay, and I'd probably need at least 2 screens to show you how that works. And it was actually taught in the Practice of Statistics, first edition. Okay, but it's not emphasized as much anymore because it's not a standard. Okay, to be able to show how a type 2 error works. Okay, so, but the relationship between a type 2 error and power is important, and you will have to know that. So know that power, which is a probability, is kind of the complement of a type 2 error. Okay, it's not kind of, it actually is a complement. So 1 minus that type 2 error is the power. And then further, the probability of a type 2 error, okay, is the same as 1 minus the power. Okay, so what's going to happen? What they'll do is they'll give you one of the two. Okay, they'll say, hey, power is equal to, 0.2615. And they'll say, hey, what is the probability of a type 2 error? Okay, and all you need to do is take this and subtract it from 1. Okay, so very simple procedure. Okay, and that would be your answer. That's as deep as it gets. Okay, all right, so here's what I have. These ideas, again, are taught in type in 9.1, 9.2, and 9.3. And so what I did is I picked a couple of the problems that existed, okay, from each of those respective sections. So this is 9.1, this is 9.2, and this bottom is 9.3. Okay, you'll pretty much do this. You'll find a null and alternative for some of these. Okay, see what they say, and they'll ask for verbal description or written descriptions of what a type 1 error or a type 2 error would be in context to what your null is. Okay, and oftentimes we write answers with respect to the HA, so that will be important to have written, as well as the definition of whether it is a mu or a p, so you'll have to define those as well. And then again, they'll ask you to explain what is a type 1 error in context of this story, and what would be a type 2 error, okay, based on whether or not you rejected the null. And then oftentimes they'll say, what is the consequence? And we talked about those with respect to Miss Moon's bowling problem. Okay, so be prepared for that. And then the small formulas that they gave you. Okay, one was how do you increase your power, which means the probability of rejecting the null when you should. Okay, that's a good thing. Those two bullets that we had earlier, increase your sample size, increase your alpha cutoff. And then again, knowing this relationship that power is equal to 1 minus the type 2 error. All right, and that is it. Okay, so there's a couple problems in each section. It looks like there's 4 there, there's 3 here, there's 2 here. Look for these answers for part A to help answer 73B and 74B. That's really just looking at the null and the alternative and deciding after you did those 5 steps, did you reject the null or not? Okay, and then you can move forward in deciding what type of error that may exist for that respective problem. Okay, all right, if you have any questions, you let me know. Thank you for your attention, and I hope you have a great day.